Okay, let's continue on with going over the homework on angular momentum and rotational kinetic energy. I believe we left off on question, what was it? Lost track. 4A, right? So we calculated the angular momentum of the Earth as it goes around the sun. Okay, so now we want to take that. This is actually a pretty important problem right here. Because, and this is the slightly elliptical, we learned a while ago, Kepler found that our orbit is slightly elliptical. In other words, the distance from the sun changes over the course of the year. We're closest to the sun in winter, at least northern winter, or furthest away in the northern summer. So I want you to use your supreme expertise in physics to ask what will change as a consequence of that that elliptical orbit. All right, will angular momentum of the Earth about the sun change? Okay. Fourth or fifth time we're talking about, is angular momentum conserved? So we have to ask ourselves, is there an external torque acting on the Earth? All right, question mark. So let's look at, okay, so now I'm going to be careful. What is our system? Our system is the Earth, not the Earth/sun. So in order to determine if there's an external torque, we got to look at whatever forces there are. So what do we have? Well, we have an F that's acting in towards the sun. Oh, okay. So what is our pivot point? Well, it's essentially the sun. And it's not quite the sun, because we know that there's a center mass is between the Earth and sun, but it's pretty much in the sun. So if that's our force, and our lever arm goes through the pivot point, then there is no external torque. So no external torque, therefore L prime equals L. Angular momentum is conserved. Okay, that's important. So as we go around the sun, we know that our orbital speed changes, but our angular momentum doesn't, because of that no torque or no external torque rule. If you try to think of this in terms of angular speed, and you know that we go faster at different points, then you might be tempted to say that angular momentum is not conserved. So avoid trying to explain angular momentum in terms of motion. It can be confusing. In fact, I'm going to jump to 3. If L prime equals L, then that means that I prime omega prime must equal I omega. And if we change our speed, therefore angular speed, then that would imply that the moment of inertia changes. Another way you could understand that is when we're far away, our mr squared value is bigger than when we're right here, where it's going to be smaller. So that implies that the angular speed is going to change. So you can use one to argue the other. In fact, I would base the moment of inertia on mr squared and then relate that to omega prime, rather than the other way around, which is how I led into that. I shouldn't have skipped kinetic energy, because that might help us understand the change in velocity more directly. Okay, so I've already alluded, the speed will change as we get change distance from the sun. Why? Well, from a conservation of energy standpoint, you can say when we're here, right, versus a small r, when we're really far away, we have a high, our UG is bigger, therefore our KE is smaller. If we're right here, we're closer to the sun, so we're deeper in the well, so to speak, so our UG gets more negative, or gets less, therefore kinetic energy gets greater. Therefore, we have a greater kinetic energy here or there. Another way you can look at it, okay, so kinetic energy, all right, KE will change. It'll get greater as we get closer. So there's two ways you can understand that. You can basically say that the change in KE is equal to the negative change in UG, right? Well, the loss in UG goes to a gain in KE. And as we get closer to the sun, our kinetic energy goes down. Okay. The other way you can look at that is work. Okay, so if I'm looking at this point here, the force is this way, our motion is that way. And what I want you to understand in an ellipse is this is not a right angle. And since it's not a right angle, there is some component of that force that is along the line of that displacement at that instant. So there's net work being done on the Earth. Therefore, the kinetic energy is going to change. So that's another approach you want to look at. So here we're looking at external torque. Here we're looking at external work. Or if you include the sun in our system, then you can look at it in terms of conservation of energy. But since it was just the Earth, we should look at it in terms of work. And since the kinetic energy will change, the velocity will change. Therefore, the angular velocity will change. All right, that's a good problem. Moving on. Back to the sun. Suppose our sun collapses into a white dwarf. That's what we believe, are pretty sure, is the eventual fate of our sun. Okay, it will basically collapse upon itself, shed most of its mass, roughly half of its mass, but in the process, because it's not going to, because it's going to collapse on itself, it's going to shrink to a tiny size, 1% of the radius. However, even as it sheds its mass, since there's no external torque in that process of collapsing, there's going to be no loss of angular momentum of the system. In other words, the shedded solar masses and the remaining white dwarf will have the same total angular momentum afterwards as it was before. So we can then ask, what will be its rotational rate when it's a tiny dwarf? Right now, its rotational rate is once every 30 days. So this is a conservation of angular momentum. So L prime equals L, and this becomes I omega prime equals I omega. So we've seen that quite a bit. So what information do we have? Well, first of all, I prime, right, the new moment of inertia is going to be 1/2 mr squared, right? Well, 1/2, the mass is going to be 1/2 the original because we've shed 50% of it, all right? And then we go to a size that's 1% of the original. So that's 0.01 times r, quantity squared, and if we do the numbers, we basically get 5 times 10 to the negative 5 times the original. Okay, if the original is 1/2 mr squared, this is going to be 5 times 10 to the negative 5. So with that in mind, we can say that our omega prime is going to be equal to the original moment divided by the new moment times the current omega. So we just found that this should be not I naught. This should be I prime. Okay, so what we have is that this is equals I over I prime is 5 times 10 to the negative 5th times the original. Okay, and omega is not 30 days, but once every 30 days. Okay, so that's what we got to be careful of. I got to put 1 over 30 for omega, just the reciprocal. So if you work that out, you get, if you solve for the new omega prime, you get 670 revs per day. So it's going to be rotating really, really fast. Interesting. All right, moving on. Ball twirled around in a string. Okay, calculate its angular momentum, I omega. You are given omega, oh that's nice, and you're given r, and you're given m. So using I omega. Okay, well omega is given, where do we get I? Again, the fact that it's a ball is irrelevant in terms of what its moment of inertia is. It's not going to be 2/5 mr squared or something like that. It's a mass that's located some r from here, so that's simply mr squared. Okay, so that's I. So we're going to have mr squared times omega. Okay, you can put in numbers and get an answer there. The other one is going to be mv times r, right? Well, you put in m, you put in, how are we going to calculate v? Ooh, how are we going to do that? Well, you could do 2 No, we don't have time. So we would have to say that that's m times, I just want to make sure, yep, v is going to be omega r, and times r. That looks a lot like what we have there. So you can see you get the same thing. All right, moving on. There's another important problem. We've got 5 minutes. Let's see if we can get through that. Oh, actually, this was done in the notes. It's essentially the exact same problem. Okay, so we have a ball hits the end of a stick. The stick can pivot about a pivot point here, and the ball does stick to the rod to make it a lot easier. It's the same mass. So I'll let you go back to the notes and look that over. I'm not going to go through all the information on that. But let me just say this. Angular momentum is conserved because there's no external torque to the system being this whole thing. Okay, the torque that the ball hits the end of the rod with is internal to the system. Work this out. That's really important. Okay, derive an expression of speed just after collision. We did that before. And I didn't ask here, but remember, linear momentum is not conserved because of an external force due to the pivot point. Okay. All right. I'm going to move on then. The wrecking rod. Now I have 4 minutes. Let's see if I can do that one. So basically what we have here is I've got a rod that's on a pivot. The pivot's right there, and it swings down eventually to a vertical position. Okay, it's free to swing down from horizontal to vertical. We want to know at the moment it's moving at vertical, how fast is the end of it moving? Okay, so I want to know how fast is this point right there moving when it gets to the vertical position before it strikes something. So I broke this up into parts for you. We want to use conservation energy to develop an equation for the center of mass. That's important. That's the whole rod is falling, but we can think of what actually drops a particular height is the center of mass. So the center of mass falls that far, and we want to recognize that's nothing more than L over 2. So basically what we're saying is what's our energy at the beginning? At the beginning, it's all gravitational potential. We're some height above this final point. When it's done, we know it's going to be rotating, but it's not falling as a whole unit, so all the energy is going into rotational. So in terms of setting up the equations then, okay, this becomes mgh, but h is L over 2. It's half the length of the rod for reasons I just explained. Now on the kinetic energy rotational side, that's going to be the generic 1/2 I omega squared. Now this requires a little bit of care for each term. So we're going to have 1/2. So what's the moment of inertia? Well, we have a rod rotating about its end, so it's going to be pretty high. You can look that up, again, in your reference tables, and that's nothing more than 1/3 ml cubed, right? The whole L is rotating. And then the omega, we're going to use a V over R. So that's going to be V squared, but our R is not going to be the full length. It's just going to be half the length of the object, okay? So that's going to be L over 2 quantity squared. Now that's a little bit of a pain in terms of the algebra, so I'm going to keep this in red. The whole right-hand term reduces, if we do it properly, to 4/3 V squared. Okay, so we'll see that the L squareds cancel out. There should be an M in there, maybe not. Oh, the M's cancel out right here. And so what I'm left on the left side, sorry, is nothing more than, oops, yeah. I'm sorry, GL. So I must have moved the 2 over to here to make the 4/3. So let me reiterate. We have GL from the left equals 4/3 V squared. So our speed of the center of mass, if we do it properly, is 3/4 G times L. Okay, now we want the speed at the end of the rod. Okay, right there. So we've got the speed of the center of mass. So how do we get it for the end of the rod? Well, we use the idea that omega is the same for both. So basically, V over r equals v2 over r2. And you do that